Hello, pre-calc students, and welcome to the first day of lesson 5.2. We will be talking about the sum and difference formulas for sine, cosine, and tangent. So far, we have this list of identities in our notes. Basically, today we're going to start adding to that. You will want to have out your unit circle because we will be referring to these angles and values today. So, first, let's talk about this. Is cosine of 90 degrees the same as cosine of 60 degrees plus the cosine of 30 degrees? Now, why would I be asking that question? Why would we even think those might be the same? Well, it comes from somebody trying to do this. So basically, can you take cosine of 90 and think of the 90 degree angle as a 60 plus 30, and then can you distribute the cosine function to just do cosine of 60 plus cosine of 30 and get the same thing as cosine of 90? Well, we can look up all three of these values on our unit circle. If you look up cosine of 90 degrees, you will see that it is indeed 0. And then cosine of 60 degrees and 30 degrees, the x-coordinate 60 degrees is a half, and at 30 degrees is square root 3 over 2. So we get this. Now, is 0 the same as 1/2 plus the square root of 3 over 2? No, it is definitely not. So the lesson here is basically that you cannot distribute trig functions. You cannot distribute trig functions. Basically, instead, we have these identities for these different trig functions. So when we were looking at, if you have the cosine of the sum of two angles, this is actually what you have to do. You can simplify it, and this would become the cosine of angle alpha times the cosine of angle beta minus the sine of angle alpha times the sine of angle beta. Then the cosine difference formula, so if you're doing the cosine of the difference between angles alpha and beta, you get the following. Notice it's very, very similar to this one. The only difference is that instead of a minus sign, we have a plus sign. Then we have similar formulas for sine alpha plus beta and for sine alpha minus beta. For sine alpha plus beta, it's sine alpha times cosine beta plus cosine alpha sine beta. And for sine alpha minus beta, the difference between alpha and beta, it's again similar to this one. The only difference is that plus sign is changed to a minus sign. Now you will see that yes, these are hard to memorize, but it is something you will have to work on. The thing I pay attention to, or that helps me, is you'll notice that cosine beta is in the same spot in all of these. You can see cosine beta is always there. And then you can see that sine beta is also always in the same spot in all of these. But then you can see that sine alpha, while it's in the same place for these two, swaps places with your cosine alpha. So the sine alpha for these ones is right there, and then the sine alpha for these ones is right there, and then it swaps places with this cosine alpha. You can see that that cosine alpha swaps places. And then the only other thing you have to work on memorizing is for cosine, these signs are the opposite, but for sine, those signs are the same. And that's how I try to memorize it, and that's something you'll have to work on. For now, copy those down and then, have them out near you while we're doing our work. So let's take a look at what these are good for. Basically, using those trig identities, you can now find the exact values of things that are not on the unit circle. So for example, find the exact value of sine 15 degrees. Well, to do that, I'm going to find two angles that are on my unit circle that it can either add or subtract to get 15 degrees. So I'm going to choose two angles. I'm going to choose 45 degrees and 30 degrees. So I'll call alpha 45 degrees and beta 30 degrees. Now there's a lot of options. Basically you can choose any two angles that have a difference of 15 degrees, like 60 minus 45 or 150 minus 135. Basically any two angles will work. So then basically what I'm going to do is I'm going to think of my angle 15 degrees. I'm going to rewrite that as 45 minus 30 degrees. Then I'm going to use that trig identity of the difference between two angles for sine. So sine of alpha minus beta is sine alpha cosine beta minus cosine alpha sine beta. But now I have identified the values of alpha and beta, so I plug in a 45 degrees for alpha there and there, and a 30 degrees for beta there and there, and I get the following. Sine 45 degrees cosine 30 degrees minus cosine 45 degrees sine 30 degrees. Now you'll notice these are four different trig functions, but they are all of angles that are on my unit circle. So I can use my unit circle to look up all those values. Sine 45 degrees is square root 2 over 2. Cosine 30 degrees is square root 3 over 2. Cosine 45 degrees becomes square root 2 over 2. And sine 30 degrees becomes 1/2. Then I'm going to simplify that. So I'm going to multiply those first two fractions together. And when you multiply fractions together, multiply across the top and multiply across the bottom. Yes, you can multiply square roots. Square root of 2 times square root of 3 is square root of 6. And then 2 times 2 is 4. Multiply those two together and I get the square root of 2 over 4. They already have common denominators. Add them together. And that is my final answer. No, you cannot subtract different square roots. That is as simplified as it gets. And there is my exact value for what the sine of 15 degrees is. That's the square root of 6 minus the square root of 2 over 4. This one is pretty similar, but it's basically going the other way. Find the exact value of this. Now, cosine 80 degrees, that's not an angle on my unit circle, nor is 20 degrees. So what I can do, though, is I can say, well, this arrangement of, four trig functions looks similar to the following identity. I have an identity that says cosine alpha times cosine beta plus sine alpha sine beta, and that's the identity for cosine of alpha minus beta. So basically what I can do is say, well, that means that alpha is 80 and beta is 20. And then what I can do is I can go over on this side and just plug in an 80 and a 20 there. So this is really asking me, an easier way to do this problem is to just do the cosine of 80 minus 20. Well, 80 minus 20 is 60, and 60 is on my unit circle, and the cosine of 60 degrees is 1/2, and that's it. Now, I'm going to start using some radians as well. Now, for some radians, we might need some help because we might not be super good at thinking of two fractions that can add together to give us this fraction of 7 pi over 12, so we've got a hint here. And that is to think of 7 pi over 12 as pi over 3 plus pi over 4, and you'll notice pi over 3 and pi over 4 are both on the unit circle, and that's why this is helpful. So what I'm going to do is I'm going to say, okay, I'm going to come up with two angles that add together to give me 7 pi over 12, and those angles are pi over 3 and pi over 4, and I know that because of this hint right here. Then I'm going to rewrite this using my identity of the sine alpha plus beta identity, and that gives me this, sine alpha times cosine beta plus cosine alpha sine beta. Then I take my values alpha, get replaced with a pi over 3, so those alphas become pi over 3 and betas become pi over 4. And now you'll notice on the right side here, all of those are values I can look up on my unit circle. So very similar to the problem we did 2 examples ago, but this time using radians. And you'll notice that when I multiply those together, I get the square root of 6 over 4 plus the square root of 2 over 4. And again, we can add those because they have common denominators. And I get the square root of 6 plus the square root of 2 over 4. And no, that cannot be simplified. You cannot add different square roots. That's it. And believe it or not, we can also use those identities to do what we're doing in section 5.1. We can use them to help us verify trig identities. Basically, right now in this problem, I have 3 different angles. I have the angle alpha, I have the angle beta, and I have the angle alpha minus beta. So what I can do is I can simplify this left side by using my identity for this. So I can say, well, instead of cosine alpha minus beta, I'm going to change that using the identity into cosine alpha times cosine beta plus sine alpha times sine beta. And then I'm going to leave everything else the same. Then in my next step, I'm going to separate this into 2 different fractions. So this part of the numerator over my denominator, and then that part of my numerator over my denominator. When I do that, you can see that this fraction on the left has a cosine beta in common. That will cancel and become 1. This fraction on the right has a sine alpha in common and will become 1. And when I get rid of those, I get cosine alpha over sine alpha. Notice those are the same angle, which is nice. Plus sine beta over cosine beta. Again, those are the same angle, which is great. And now you can see that here's cosine of angle alpha over sine angle alpha, which is indeed equal to cotangent of angle alpha. Plus, and now I've got a sine beta over cosine beta, and that's equal to tangent of angle beta. And now both sides are exactly the same. And going into our last example here, basically here's two different ways to write the same information. So let's say I'm given that sine alpha is 12/13 for some quadrant 2 angle alpha. Well, another way that could be written is that sine alpha is 12/13, and now this notation here means alpha is between pi over 2 and pi, which is quadrant 2. And then this information can be written this way. Basically, you could see this problem written either way. They mean the same thing. Then what I'm asked to do is find the exact value of both of these. Well, here's what I'm going to do. I'm going to take and start here with A, and I'm going to find sine of alpha plus beta by using the identity. Sine alpha times cosine beta plus cosine alpha times sine beta. Well, you'll notice something. These two things I have in parentheses here, those are actually given to me right here. So sine alpha is 12/13, and sine beta is 3/5. That's the information I'm given. Which means sine alpha becomes 12/13 and sine beta becomes 3/5. The problem is I'm not given these two, cosine beta and cosine alpha, which means I actually have to go off to the side and do a little bit of work here. So I'm first going to find cosine alpha, and here's the way I do that, is I take what I know about angle alpha and basically I draw it. So here's what I know about angle alpha, is that it has a sine of 12/13 and it's in quadrant 2. I'm trying to find cosine alpha. So what I'm going to do is I'm going to, and you hopefully remember problems like this, I draw angle alpha in quadrant 2. I label the opposite side and the hypotenuse as 12 and 13. I do the Pythagorean theorem to find the value of this side x. And since it's in quadrant 2, I know it has to be negative. And now the cosine of angle alpha will be -5/13. I then take that fraction and plug it in right there. Oops, there's the final answer. Now I need to do the same thing for angle beta. So I take what I know about angle beta, is that the sine of beta is 3/5 and that beta is a quadrant 1 angle. So I draw that in quadrant 1. I label the 3 and the 5. I use the Pythagorean theorem to find that x is 4. I then identify that the cosine of beta is 4/5, and that gets plugged in right there. And then I have everything I need. You can use your calculator, type that all in, hit enter, and then you can have your calculator change that back into a fraction, and you get, there's my answer, 33/65. Now the good news is, for part B, is that I've done all the extra work that I need to do. So all I need to do is identify the identity needed for cosine of alpha plus beta, and then these two on the right are the ones that I was given in the problem. These two on the left are these that I already went and found off to the side, so I already have them. I just plug them in. I can use my calculator to evaluate that, and there's my final answer, -56/65. You'll notice that these problems are quite a bit of work. You got to use these identities, and then you got to do basically these two different times. You have to do something like this to find the missing trig value and then plug it in. But then once you've got all 4 values, you can use your calculator to evaluate and simplify. So that's it for the first part of lesson 5.2. Tomorrow we will be doing the second part of section 5.2.